Finding aluminum chips in every crevice of the garage, in my hair, and even in my bed was enough to drive me crazy, and more importantly, my wife crazy. So in this video, I'm going to finally fabricate an enclosure for my CNC mill. There will also be a couple other upgrades, such as swapping out the single nut ball screws on each of the 3 axes for double nut ball screws, which will improve accuracy of the mill. I will also upgrade to a flood coolant system, which will increase tool life and result in better surface finish on my machine parts. But the bulk of this video will be plasma cutting and welding a steel enclosure that will weigh about 1,000 pounds. So stick around to see my largest fabrication project come together.
Dr. D-Flo.
Let's take a look at the 3D model first to see the design and discuss my rationale behind some of the features. Perhaps the first thing you noticed is how beefy this design is. There's plenty of room for stock material and future upgrades such as an automatic tool changer. The weight and rigidity of this enclosure should eliminate the vibrations that were seen with the flimsy stand that comes with the mill. The mill will sit in the center and the table will be accessible through this sliding door. The 2 panels on either side of the center door will be hinged to allow for the mill to be installed and to load larger pieces of stock material. During a cutting operation, flood coolant will wash chips away from the part. Coolant and fine chips will find their way down these holes on either side of the base of the mill into this drawer, which will sift out the fines. The coolant will be collected in a reservoir at the bottom of the enclosure before being recirculated back up to the spindle. The enclosure will be constructed from plasma cut sheet metal that will be held together with slots and tabs before being permanently welded. This approach does not require a metal bender, which I don't have, but is also the reason why this design can best be described as blocky. You may notice that the enclosure is asymmetric, with the right side being longer to accommodate the X-axis motor on that side. Perhaps you want to copy this design, but your motor is on the left side, or you have a different size benchtop mill. Well, during the design process, I parameterized most of the dimensions that you may want to change. Here you can see that by adjusting a couple numbers, I can stretch the right side out further and change how deep the enclosure is. These are just a couple knobs that you can turn to make this enclosure fit your needs. This model is freely available on my website, and I'm considering offering kits for those who do not have a plasma table large enough to cut out the pieces. Send me an email if you're interested. But let's start plasma cutting. So I just finished plasma cutting 4 of those 4x8 sheets that maxed out the cut area of the plasma cutter. Those sheets were 1/4 inch thick, and that left me with this 800-pound jigsaw puzzle, which I'm going to assemble and weld together. I picked up 4 of these heavy-duty casters that not only have a wheel, but they also have a leveling foot. This will allow me to position the very heavy enclosure anywhere I want in my garage, and then ultimately lift it off those wheels and get a nice level base. Now these casters are going to attach to the perimeter of the enclosure. Now these right angle assemblies right here are going to be what the casters attach to. I'm going to be using MIG, specifically pulse MIG, in order to quickly and cleanly join all of these plasma cut parts together. It's been a while since I've fabricated anything, so definitely don't look too closely at my technique. But fortunately, the welder that I'm going to be using, if I drop down here, is the HTP ProPulse 220, which saves all the settings inside of the machine. And this is going to get us pretty close to perfect, even though my technique is not very good. So let's look at the settings here. We're going to be welding mild steel with 030 wire. Our gas mixture is going to be 90% argon, 10% CO2, and we're going to be on pulse mode. And that's what's going to prevent all of that splatter that you would normally see with MIG welding. We need to change our wire feed rate in order to match the thickness of the material. We're going to increase this to about 1/4 inch, as high as it goes. I've done some practice welds and found that a 0.5 volt positive offset, which increases the arc length, gave relatively good results. And with that, we can get started. right, so this definitely turned out much bigger than what it looked like on my computer screen, but that's the point. I wanted an enclosure that was spacious and I never had to worry about having an interference issue with my vise, the part on the vise, or the motors. The next thing we need to do is brace the top of the enclosure with this rectangular tube that is 3 by 1.5 inches. It'll slide right through these rectangular holes. I have 2 more pieces of that tube, which will run perpendicular. And this is what the mill will actually rest on. The front and back plate will hold these 2 pieces. So the front and back plates went on nicely. I went ahead and welded over the tabs and grinded them down just to have a nice smooth surface for painting. I also welded the rectangular tube stock to each other as well as to the vertical upright pieces. Next, we need to construct the basin, which is going to collect the chips and allow the coolant to return back to the stand where the reservoir and pump are going to be at. The perimeter of the basin is going to be fabricated from this 1 by 1 inch square tubing. The basin is going to be supported from the side of the stand with these pieces that I'm calling the wings. Here we have my cheat sheet for the basin as well as the top of the enclosure. The base and the top are separated by these vertical supports. And then if you remember from the CAD model, we've got 3 doors. The left and right doors are hinged. Those are only going to be opened when I've got really large stock or when I'm actually putting the mill into the enclosure. And then we've got the center door, which is going to slide on a set of rails, which is what I'm going to be using normally to put work into the vise. And with that, we can get going. I've got the top of the skeleton welded up, but before I installed that, I had to insert the basin plates. You can see there's holes here, which will allow the coolant to return back to the reservoir, and hopefully it'll keep out some of those bigger chips. Now I need to keep the rest of the chips out of my garage by plasma cutting and installing the sheet metal that's going to go around the perimeter as well as the doors. So I've drilled and tapped the perimeter of the enclosure so that I can bolt the sheet metal directly to it. Now during painting or during transportation, I can remove the panels so this thing doesn't act as a giant wind sail. These cutouts right here will be for either safety glass or polycarbonate, nice viewing angle from the side. And that basically takes care of 3 of the 4 sides. I just need to grind down some of these edges to make everything flush, but we'll get to that. You may have seen other DIY enclosure designs online, and most of those employ some kind of aluminum extrusion assembly for the top of the enclosure. There's usually 2 reasons for that. The first is that it's really easy to drop down a piece of 1/4-inch acrylic or polycarbonate down the slots of the aluminum extrusion. And the other reason is that it's easy to get the extrusion perpendicular and parallel to each other where it needs to be. And one of those places is where the door will be hinged at. I, of course, was in the welding mode, so I decided to make everything out of this 1x1 square tubing. And what I didn't realize at first is how difficult it would be to get this perpendicular and ultimately parallel with the door. So now I'm going to work on the doors, weld on some hinges, and we're going to be pretty close. I changed my choice of hinges at the last second. I went with these bolt-on hinges that have a slight amount of play up and down. This is great because it keeps the door resting on the base, which will keep coolant and chips from coming out right here at this seam. But when I need to load a large piece of stock material or insert the mill for the first time, I just lift up and the door swings out freely. For the sliding door, I went with drawer slides. And I have to admit, this was a solution that I was trying to avoid because 1, they look a little bit tacky on the outside, and 2, on the inside, they can get jammed up with chips. But this was the best thing that I could come up with on my budget and still preserving the ability to open up the front of the enclosure entirely without having a cross beam. I'm going to have to install some bellows on the back side here just to make sure that the chips don't interfere with the motion of the ball bearings. There's still a couple things left to fabricate, such as the door for the coolant reservoir portion down here, as well as a tray for the fine chips that make it past the mesh holes in the basin. But those tasks are independent from painting this thing, which is something I really want to knock out before I lose the weather as well as the long days. Anything that's going to be near a milling machine is going to experience a lot of wear and tear, not only from the repetitive hitting of the chips coming off the cutting tool, but also just from accidents on my part, such as dropping a sharp part into the basin. And because this whole thing's made out of steel, we don't want to expose any of that raw material because it's going to rust. So for ultimate durability, I went with an epoxy paint, which chemically cross-links, resulting in a very hard coating. Epoxies are also great at filling small gaps and voids, so I'm hoping to get a really smooth finish on the mill. For the color, I went with white. I just wanted something that's clean, that pops. It's going to look really good when I include some red accents, which we'll get to later. I've got a couple different products down here. I have an epoxy-based primer, the white epoxy paint, and spray cans of both the primer and the white paint for tight spots within the enclosure. I purchased the primer from McMaster-Carr, and in their attempt to be as vague as possible which brand you're actually getting, they sold me a paint that's spray-on only, even though the description said that it can be painted or sprayed on. I realized this a little bit too late. I'm still going to paint it on. It's going to be a little bit thinner. This, of course, is going to be the primer, and it's going to be covered up by the white epoxy paint. One of the drawbacks of working with epoxy-based paints is that you have to mix an activator with the epoxy. Now, you have to be sure that these two components are mixed really well, or you may have incomplete curing, which will result in a very tacky feel to the finish, which is not good. Once you mix them together, this starts a timer, and you have to apply the paint in, I think for both of them, 2 hours, or else it'll start to harden and you won't be able to apply it. So I'm going to mix these up in smaller quantities so I'm not rushed. So my enclosure has arrived at my now very crowded garage. It's difficult to even get this thing fully in the frame. In preparation for moving the mill to the enclosure, I've taken everything off that can be carried away by hand. I even dropped the spindle because I'm going to replace the oil seal and bearings. A common issue with this mill is how hot the spindle gets. After about an hour of runtime, the outside casing reaches about 63 degrees Celsius or 145 degrees Fahrenheit. Not only does this high of a temperature make it difficult to handle tools as I'm changing them out, but it also shortens their life. The bigger problem is that if the temperature is this high on the outside, then the spindle bearings must be toast. Except they weren't. I frequently checked the run out of the spindle and it was always less than 5/10. This matches up with the ±2/10 advertised on the Precision Matthews website. For this measurement in particular, I'm using a cheap imported collet, so the spindle runout is probably a bit less. The prevailing theory on my forum is that the oil seal is too tight for this model, which is causing the excess heat. And let me tell you, it was a pain in the butt to get this seal out. I had to resort to the drywall screw method where I drilled a coarse screw into the seal and tapped it out with a screwdriver. Not the most elegant method when working on a precision machine tool. I purchased an oil seal with a slightly larger ID, which will help with the heat if this is the root cause. For the bearing swap, I had to order a press, which is one reason I waited so long to address this problem. The press is running late, so I will cover that spindle work later. The big upgrade to the mill, besides the enclosure, is swapping the single nut ball screws for double nut screws, which, as their name suggests, have 2 nuts per screw with a spacer between the two. The spacer puts a preload on the nuts that causes the ball bearings in one nut to sit on the opposite side of the thread as the bearings in the other nut. This eliminates backlash or play and should improve the precision of my mill, even though I had software compensation for the backlash present in my single nuts. I'm also upgrading to sealed angular contact bearings which support the ball screws on all axes. With the open bearings that were provided with the conversion kit, small chips would get into them and affect their motion. The new angular contact bearings are sealed. Finally, while I have the mill apart, I'm going to upgrade the lubrication system so that I can control how much oil goes to each linear way and ball nut. With the current configuration, about 80% of the oil goes to the y-axis. Because this way is at the lowest point, the oil flows there the easiest. I have to pump the handle a couple extra times to lubricate the z-axis sufficiently. Not only does this waste oil because it's just pooling on the Y way, but when running flood coolant, more oil will need to be skimmed out of the coolant reservoir. This new manifold will allow me to adjust how much oil goes to each lubrication point. I'm also going to use proper fittings for connecting my oil lines to the ball nut. I had previously just stuck the flex line that was feeding the original lead screw into the lubrication port of the ball screw. Before we jump into the time-lapse of these upgrades, I also want to point out that this chip drawer opening was driving me crazy ever since I plasma cut it. The height of it was simply too small for it to be of any use. Off camera, I used my angle grinder to widen it an extra couple inches. Now, of course, more chips can build up before I have to open it up and clean it out. And with that, let's get to work. Are you impressed with the progress I've made so far? Terrible pun aside, my 20-ton hydraulic press has arrived. Both my press and my engine hoist are from the same manufacturer, and I've been very happy with their quality at an entry-level price point. Check out my Amazon store, linked below, for the press, hoist, and other fabrication tools used in this video. It's time to put the spindle back together, and I must admit that replacing the bearings is what I'm most nervous about. Of course, messing up this swap will severely affect the accuracy of the mill and the life of my cutting tools. I searched for YouTube videos and guides on this process, and my findings can largely be categorized by two approaches. The first is what I describe as the surgical precision method, which involves a lengthy process of cleaning, massaging the lubrication into the bearings, and setting the preload just right as to optimize stiffness and RPM rating. There is no doubt that the surgical precision approach will result in increased spindle performance and bearing life, but honestly, I don't have the tools, patience, or know-how to go this route. The second approach I'm calling the job shop method, where time is money and the mill just needs to operate reasonably well. I would be satisfied if I could achieve that previous 5/10 run out without the spindle overheating, which I think can be achieved with the job shop route. As mentioned earlier, my hypothesis is that the tight oil seal is causing the excess heat, but also too much grease in the bearings packed at the factory could also be an issue. If the lubrication takes up more than 30% of the free space, well, then we can get excess heat. I'm using Kluber Isoflex 15 grease, and there's nothing precise about this, but I am trying to keep the grease on the lower end, closer to that 30 to 25%. With the bearings greased, the last important consideration is their orientation. We want the marked faces to be facing towards each other to give us a back-to-back configuration. I'm sure that the comments on this video are going to be packed full of great information, so check that if you've got any other questions, or it's best to check it just in case I make a mistake. back together, I'm working on the preload. We don't want it to shift in the housing here. So I'm going to tighten this nut. You've just witnessed the creation of a third approach for installing spindle bearings, the moron method. This would have looked a lot more professional if my special order of aluminum tubing didn't get lost in the mail. I spec'd this aluminum tubing so that it would clear the spindle nose but sit on the inner and outer races of the bearings to get a nice even force when pressing them into place. The absence of this tubing is no excuse for pressing on the spindle nose. I also can't believe how crooked I had the quill housing when installing the back bearing. It seemed straight when I was looking at it, but the video revealed otherwise. If all that wasn't bad enough, I accidentally dropped the spindle when I was flipping it around. The only consolation was that I mopped the floor the night before, so I didn't have to pick a bunch of grit out of the bearing. It seemed like the assembly was spared from any obvious damage. To salvage some credibility, I took an indicator reading of the inner bore, revealing less than 5/10 runout. Anyways, if you're nervous about replacing your spindle bearings, this is about as bad as it can get, and it seems like I still have a functioning spindle. Let's go ahead and get it back into the headstock before I drop it again. With the enclosure buttoned up and now level, I can show you why it needs to be so large. The PM833TV mill has 22 inches of travel on the x-axis. And you can see here, to get to my tool setter, I have to kick the table all the way out. Now, a lot of designs online, they make like a little flap here that allows the motor and some of the table to go out when you're on the extremes of the travel, but I'd have to leave that space clear in my garage anyway, so I just decided to make this thing probably a little bit bigger than it should have been, but I don't have to worry about anything sticking out of the enclosure. This thing is completely enclosed at the extremes of its travel. With the parametric CAD model of the enclosure available on my website, you're more than welcome to make it as small or as large as you want. I also want to draw your attention down here to these buttons that I added. We of course have the emergency stop button, which, stop the mill when things are misbehaving. Then next to it, I've got the button for controlling these LED panels that point right at the machine tool, which is very useful. Over here, we've got the first button is for the power drawbar. And the second one will be for triggering a washdown hose, which I haven't configured yet, but that'll be great for kind of cleaning off excess chips. But I know I've gone through all of these components relatively quickly. I basically reassembled the entire mill, went through all the upgrades in a very short duration. So I want to remind you that I have YouTube videos on all the different upgrades and more information on my website. So definitely check that out if you haven't yet. Before turning our attention towards the flood coolant system, I want to let you know that I will be working on YouTube full-time during this upcoming summer. Since the inception of this channel, I've been slow to release videos because I'm packing in the planning, building, filming, and editing after work and on the weekends. With my attention solely focused on YouTube, I will be able to upload more regularly and tackle even larger projects. This summer will be a trial run for future summers, so if you want to ensure its success, consider becoming a channel member here on YouTube. Not only will your support bring more content to this channel for everyone, but you will also have access to member-only live streams where I take you behind the scenes on my most popular projects. To become a member, hit the join button below this video. But okay, let's turn our attention to one of the main benefits of having an enclosure, the ability to run flood coolant. For over 2 years now, I've used a minimum quantity lubrication or MQL system, which aerosolizes a small amount of coolant and delivers it to the cutting tool with compressed air. For the hobbyist operation, MQL definitely improves the life of my tools and surface finish of parts by coating the cutting interface with a thin layer of lubrication that kept everything running cool and smoothly. Nearly all the coolant evaporates off the workpiece and does not need to be recaptured, which of course is what allowed me to use it without an enclosure. However, the ability of the MQL system to remove previously cut material to prevent it from being dragged along the work surface or cut a second time is relatively limited, especially because the chips tended to stick to the lubricated surface. Flood coolant systems address this problem by maximizing the amount of coolant that washes over the part during the cutting operation to carry away all chips. To deliver large amounts of coolant, here is my 1/4 horsepower coolant pump and 9-gallon reservoir. This will sit in the bottom of the enclosure and pump coolant up to the cutting tool. I've created a quick diagram to show you the path of the flood coolant. Exiting the pump, the coolant will flow through a pressure gauge before entering a micron filter that will remove any microscopic chips that would otherwise build up and cause flow issues down the line. After the filter, the coolant will go through a second pressure gauge, which will be used in combination with the first gauge to determine when to change the filter based on the pressure drop. Next, the coolant will go through a manifold where it can go one of two directions. The first is a pressure release valve that will return coolant back to the reservoir. If the second path out of the manifold is blocked, the pressure relief valve will ensure that the pump is always moving coolant to prevent strain on the motor. Also, while unlikely, if too much coolant is coming out at the workpiece, I can decrease the pressure here. The second path out of the manifold leads to a 3-way valve, which will direct whether the coolant goes to the washdown hose or the mill headstock for blasting away chips during the milling operation. Coolant leaving from both the washdown hose and the lock line near the spindle will return to the reservoir through the chip drawer, which will have a fine mesh installed. I'm going to work through all the plumbing now, and then we're going to come back to the chip drawer. Next, we need to get the coolant out of the basin and back to the reservoir to keep everything flowing. I have drainage holes running along the entire width of the enclosure. This is great for increasing the drainage area, but problematic because it means that I need a chip pan that is equally as long. The best way to produce this long of a chip pan would be to bend and weld sheet metal together. However, I do not have a 4-foot bender, which would be required to make a pan this large. What I do have is a massive 3D printer, which is literally right here. Let's take a quick look at the CAD file for the chip pan that I've designed to be printed on my large format 3D printer. Up top, we have a collection area for fine chips. In the center, we have a lip for a large mesh to sit, which will filter out the fine chips. On the other side of the mesh, we have a gentle slope to concentrate the coolant and funnel it back to the reservoir. Let's send this file over the printer and hit start. There was only one issue with the drawer, and that's these divots that formed. I used too light of an infill. I was really worried about this drawer being too heavy. It's probably about 25 pounds right now, which is nice, but that light infill caused some areas to sag. So I just filled those little, I guess, potholes with some hot glue. But generally, it's difficult to get a watertight seal with material extrusion 3D printers, so I'm not going to rely on this to be watertight. I'm going to use some automotive 2-in-1 primer. This goes on really thick and it's going to fill any voids. But first, we need to do a test fit of everything just to make sure that this works before we go to the hassle of spray painting it. So, as you can see, the inside that's going to be underneath the mesh is going to slope down here to this drain. It's important that we're able to then connect a tube there so that we can take everything and collect it and have it go right into the reservoir. So I've printed this plate. It's got a barb on it, a 1-inch barb. This goes here. This other tubing will go on there when I'm ready for it. But we can't obviously install this until after it's inside the drawer. Last thing I want to check really quickly is, does the mesh fit? Cool. And obviously we'll seal around the edges. We'll come back to that. The moment of truth, is this going to fit into the mill enclosure? Nice. There's a little bit of a lip right here, but I'd rather this thing be longer than shorter. Next, we're going to go ahead and get it spray painted. I'm not going to spray paint the outside edges just because I like the way the layer lines look, and obviously the red matches the other accents on this mill enclosure. Overall, I'm happy with how the enclosure and the chip drawer are able to recapture the coolant. About 98% of it's making it back to the reservoir. The small amount of lost coolant is taking an alternative route where through surface tension it can track across the rectangular cross members. I've updated the CAD model to not have holes in the basin where the rectangular tube stock is at, but I will use some sealant off camera to fix this issue on my current model. It's been a long time coming, but it's finally time to make a part. For my first project, I'm going to create an aluminum tray for the left side of the enclosure. This tray will incorporate these one-way needle roller bearings, which will allow me to tighten and loosen end mills in these TTS holders with only one wrench. Normally it requires two. In addition to the roller bearings, there will be a large pocket in the back for wrenches, Allen keys, and other commonly used tools for fixturing parts in the mill. And on the right side, there will be a couple of holes so that I can store tools in the order that they will be used. I'm actually going to leave you with this milling montage, so if you enjoyed this video, please hit the like button, subscribe if you've not already, and consider joining as a channel member. And with that, I'll catch you in the next one.